Hi. Thank you both.
Don't shut up.
I know.
First.
Yes.
Success is not guaranteed.
That's right. We're on our way.
I managed to move things around so that I can still.
Fantastic.
Yeah, it's wonderful up there in Australia. It's basically impossible to like meet with them.
So you have dongles for USB-C, HDMI?
We will in just a moment.
Okay. You should probably try
Should I
this.
go to Mark's office or is he coming in?
You were trying? Yeah. So I can plug in? Yeah, I think so. Right, all good.
I heard that with the server song.
Never seen it.
Rising.
Okay, so let's get started. It's my pleasure to introduce someone. Oh, that's fantastic transition. Someone who needs very little introduction here at the CFA, Jeremy Drake. Jeremy did his PhD at Oxford. He's been here at SAO since 1995. Sorry. So that's what you know. What you don't know is that if you Google Jeremy, or maybe you do, the first result is actually Jeremy J. Drake, astrologer, right on Garden Street. So you have an alter ego, but no Google reviews. So if the predictions from today's talk sort of pan out, maybe we can all give you a positive rating on Google.
I guarantee it'll be as equally as realistic as astrology.
Right. Okay. So with that informative introduction.
Well, thanks very much, and thanks for the opportunity to talk today about coronal mass ejections in stars. So, coronal mass ejections, here we are. This was a quite remarkable period of activity for the Sun, 1999, seen by SOHO. You see all those CMEs going off, and this was a period of only a few days. CMEs launching essentially continuously. So, the problem is that we cannot see these things in other stars. As I speak to you now, there is not yet a definitive detection of a coronal mass ejection in a star other than the Sun. But why do we care? I mean, these things are tiny sort of amounts of energy for the Sun, right? It's not really a macroscopic thing that we care about, you would think. Well, we sort of care about them a lot more, apart from just the physics of how this scales to other stars. We sort of care about them for these things now, which maybe we didn't sort of 20 years ago. So Proxima B, of course, the artist's impression, somewhat optimistically rendered with surface water that's liquid here. But unfortunately it resides close to this fellow here, which is Proxima Centauri, which is an active flare star, of course. Active flares, it should have coronal mass ejections. And indeed, this was the most recent, quite spectacular flare from Proxima Centauri. This, the one here, seen in visible light flare. Several magnitudes it went up. This actually reached what they claim was a limit that you could actually see with the naked eye if you looked very carefully on the dark sky. So huge flares. And we expect coronal mass ejections because on the Sun, that's what we see. What we're looking at here is the CME association rate as a function of the peak X-ray emission in GOES. Okay, so this is X-class flares in GOES, M-class flares. And you see, as we get up to X-class flares, essentially every flare has an associated coronal mass ejection. So big flares always have coronal mass ejections, or essentially nearly always. So, some questions come to mind. Can we just extrapolate what we know about solar coronal mass ejections to active stars, to stars other than the Sun? If we can, then essentially our job's done. We just take the solar observations of CMEs like these, and we extrapolate away, and there we get our relationships for active stars. When we start to look into that, we get to this question here. What fraction of L-bol can dynamo activity extract? This is not really a question you'd expect from this, but it actually turns out to be a question that comes up. So why is that? I'll get onto that. But sort of, I suppose, the bottom question here, CMEs and active M-dwarfs are close-in planets doomed because of CME activity. So some questions here for CMEs on stars. Well, first of all, let's look at the CMEs on the Sun. And what we're plotting here is the mass of CMEs against the X-ray integrated energy of the associated flare along here, mass along here, from Yashiro's compilation. And you can fit the average. The average is these green histogram in different X-ray energy bins, and that fits quite nicely with a power law relationship. Slightly less steep than direct proportionality, which is this dashed curve here. You can do the same for kinetic energy. Again, power law sort of slope fits the mean very nicely. Now what we plotted here is the proportionality, but it's the equivalence. It's actually saying, what if CME energy was equivalent to X-ray flare energy? And that's this relationship here. So you see that CMEs are somewhat more energetic than the X-ray flare. They're actually 100 times more energetic on average than the X-ray flares. So every time you see a powerful X-ray flare on the sun, you have 100 times that energy expended in that X-ray flare coming out in your kinetic energy for your associated coronal mass ejection. And that has quite important implications. And it has implications because when you look at an active star, this one is EV LAC and M dwarf in X-rays, you see flares. It's essentially flares on top of flares, on top of flares, on top of flares. The whole thing is essentially flares. You can essentially approximate these light curves in X-rays almost 100% as being due to flare activity. So it's all flares. What we're seeing is all flares in the X-rays, essentially, to a good approximation. It turns out that you can approximate this flare frequency as a function of the energy of the flare as a power law, the same as it's been done with the sun commonly. So number of flares per unit energy, energy to the minus alpha, where alpha is some sort of power law index. That's about 2-ish. So why is this important? Well, what we can do here, we know that all the X-ray flux is in flares. We know that we have a power law relationship on average for the sun. We can just take that power law, we can mix it with the power law for the flare frequency and integrate it to get things like the mass loss rate in coronal mass ejections. And the mass loss rate is going to be proportional to the X-ray luminosity of the star, and then it's got things like the indices for these power laws for the flare frequency and the mass. And we can integrate this out. This is the limits of integration, the weakest flare, the strongest flare. And then you can plot that up as a function of Lx of your star. And that's what we're doing here. So this is CME mass loss rate here and X-ray luminosity along here. So does this make sense? Okay, let's see whether this makes sense. The sun is currently around about here, around this bottom corner, 10 to the 27 X-ray ergs per second. And we get a few 10 to the minus 16 solar masses per year. This actually is reasonable. If you integrate all the CMEs from the sun over a few years' time span, divide by the time, that's the mass loss you actually get. So that actually makes sense. But what about the sun when it was younger, when it was much more X-ray luminous? And when it was younger, it was X-ray luminous by factors of 1,000 to 10,000. So we're now down at this end of the plot. And what's our mass loss rate? Ooh, we're up at 10 to the minus 10 solar masses per year. 10 to the minus 10 solar masses. So the sun was very active for a few 100 million years, maybe up to 1 billion years. If we integrate that up over 1 billion years, we've got several percent of the solar mass in coronal mass ejections. Several percent. That's huge. That's actually really, really interesting because it actually solves the faint young sun paradox. Those of you not so familiar with this one, is Carl Sagan first realized this, that the sun early in its evolution on the main sequence was too faint to maintain liquid water on the Earth. So what was going on? What's the solution to that problem? There's been myriad suggestions of that, but one of them is that the sun was actually more massive when it was younger, and it's actually lost a little bit of mass, and so it's more massive, it's more bright. And so that solves this paradox, which has been going on for decades. So we've solved it. It's all CMEs, right? Excellent. Oh, what's this? On the road to success, there are no shortcuts. Oh, bother. So we're missing something out, maybe, are we? What could it possibly be? What are we forgetting? Damn, the bloody laws of physics. Damn, there's something, always some little thing that gets in your way, isn't there? Stops you from that success that you're striving for. Laws of damn physics. So what laws of physics are we forgetting? Well, I showed you the plot for mass integrated as a function of X-ray luminosity. We can do the same for kinetic energy. If in doubt, follow the energy. And here is the plot. And so we're plotting here the CME kinetic energy loss rate against the X-ray luminosity. And let's look at our very active young sun that solves the thing for coronal mass ejections. And ooh, this is like fractional L-Bol. So this is now several percent of the luminosity of the sun. Okay, so we need several percent of the luminosity of the sun in coronal mass ejections. Does that work, anyone? Well, the energy comes from the dynamo, right? It's a magnetic dynamo. How much energy can we scavenge with that dynamo to put out in coronal mass ejections? Well, if you ask dynamo-y people, they won't give you a straight answer. They won't say, oh, no, it's going to be 10 to the minus 3.6 or something. They won't give you a straight answer to that because no one really knows. But if you ask them, could I get out 10%? They would say no. No, 10% is way too high. Okay, so we have an energy problem. 10% is way too high. to get out of the dynamo in coronal mass ejections. So what could be going on? Well, so I started thinking about this a little bit more through an act of foolish naivety. Well, actually, one of many acts of foolish naivety, but this is the particular one that got me thinking about this, and that basically we just started to do CME on an active star. I said to Arthur Cohen, who was here at the time, said, we have to look at CMEs on active stars. Let's set CMEs going on AB Dor, on our model of AB Dor. So AB Dor is a very young active star, half-a-day rotation period, for which we have a good ZDI Doppler imaging magnetic field surface map that we can use to drive our space weather MHD code. So we can set a nice, really energetic solar CME that's located just here, let it go on AB Dor. And we're sort of expecting to see these magnetic field lines open up and everything is going to look spectacular and fantastic and we'll have a brilliant movie. And then it looked like that. So basically nothing happens. You see that like it tries to escape, but the overlying canopy of magnetic field is not broken. It just doesn't escape. So, you know, the solar people in the audience are sort of thinking, well, you fool, Drake. We know that this happens because it happens on the sun. This is active region 2192. Just one of several have been studied for CME suppression. 6 X-class flares, of which, from that plot previously, should have all had CMEs, but 0 were observed. And here's the fellow here. And the reason is that it has this strong magnetic canopy overlying it. There's the active region there. So essentially the CMEs were all suppressed. Nothing came out. So we know that CME suppression sort of works, but how do we apply these sort of qualitative observations of things that happen on the sun and to something like an active star? We need some sort of prescription. So what we have here is a loop that's a current-carrying loop, coronal loop in the sun, current I. This is essentially the mechanism that Titov and Demoulin used to sort of demonstrate a coronal mass ejection sort of mechanism. So this sort of thing is unstable. It's sort of a bit like if you take, I don't know, something like this coffee stirrer and so I sort of spring it in. Well, there you go. That was a pretty weak CME. But it's the same sort of tension force that causes that thing to erupt and want to expand. But if you put an overlying magnetic field over the top, you can prevent that, and you can work out what is the current required through this loop, given the magnetic field, to actually do that. And then because it's an inductor, you can work out what the energy is quite easily. And then you can plot that all up in a nice plot of threshold energy against equatorial field strength of a star. So threshold energy means that this red curve here is the point at which CMEs are just about on the point of being able to escape. So above this bit here, CMEs escape. Below, they don't escape. So does this make sense? So this is the range of solar CME energies. The solar large-scale field sort of varies around here. Yeah, most of them escape. Some may be trapped, but most of them escape. So that seems to make sense. Okay, so when we go to active stars, we're down at this sort of kilogauss field strength. What happens to solar CMEs? None of them will get out. So this predicts essentially that no solar CMEs would ever escape from a very active star, if they were on the equator, of course, which they're all probably not. So some escape, but most of them, most CMEs that we know on the sun, are probably going to be suppressed. Okay, so how do we test this? Well, we need to do a little bit more testing, because that was a very, very simple model. So let's throw another supercomputer simulation at the problem. So here we have active region on the sun from a solar magnetogram. And what we did here was slap on this 75 Gauss dipole on the top, right? So solar magnetogram, sort of like a few Gauss large-scale field. We slapped on a 75 Gauss large-scale field. And then Julian, sitting here, spent hours and hours of German supercomputer time to simulate CMEs on it. And this is one. And what we can do here, we can tune the energy of that CME. And this is one that didn't escape, totally confined by the overlying magnetic canopy. And then we can sort of gradually bump up that energy of that CME until we get something that looks a bit more interesting. And here it is. This one does escape. Okay, so we can work out what the threshold energy of our CME and potential energy is, about 3 times 10 to the 32 ergs. Okay, so let's go back to our very simple analytical estimate here. How does that look? Okay, so we've got 75 Gauss dipole about here, 3 times 10 to the 32 ergs. Wow, look at that. Now, what happened the last time when we solved a problem with, I don't know, it was like a ghost of that thing, but I still haven't worked out what's wrong with this, but there's bound to be something wrong. But if this picture is actually reasonably correct, then basically it is telling us that we have a reasonable estimate of the suppression rate for active stars. So now what we can do is we can go back and we can say, okay, we did those earlier integrations over large energy ranges of flares, okay? We went from very small flares on the sun to very big flares on the sun, or very big flares on stars. What happens if we collapse that range of integration so that we suppress out all of these lower energy CMEs and redo that? Do we solve our sort of energy problem? So what we're looking at here is that plot again for the red is for alpha of 2.25, which most active stars seem to have this power law index. The black is the original one. So, well, it sort of helps. You know, we get a factor of 3 or 4. It's not like, no, it's not, you know, it's not brilliant, is it? The grey, by the way, is if you change that index of the power law to plus or minus 0.75. So it helps, but it's probably not the whole answer. I don't know. This is telling us that very active stars still need 1%. 1% of L-bol has to be expended in magnetic energy of CMEs. That's a constraint. I don't know if it's realistic or not, but it's about 1%. What happens to the mass loss rate? The mass loss rate goes down a little bit. We're now sort of down in a regime where it probably doesn't solve the faint young sun paradox anymore, but physically probably more realistic. So what do we have to do now? Well, we have to try and observe CMEs, obviously. We can't just go with this sort of very hand-wavy sort of theory stuff. We actually need real CMEs that we can get our hands on and analyze them. But as I told you, we have never detected definitively a CME on another star other than the sun yet. There are some suggestions, though. This is one of the biggest flares ever observed on a star. It was observed on the close binary Algol. And here we have the count rate seen by the Bepo-Sachs-Mex instrument. And this thing was absolutely huge. This is time in seconds. So here we have like a day here. We got 2 days. This whole thing lasted 3 days, 3-day flare, enormous amount of X-ray energy. But more interestingly, perhaps, it had this interesting absorption signature associated with it. If you looked at the column of hydrogen in the way of that flare, it sort of looked like this. It decayed from quite a high value quite quickly over a period of about 50 kiloseconds. Now, the flare location was actually, I forgot to point out, but it was actually eclipsed by Algol A, which is X-ray dark. And so the location of the flare and the size was actually quite well determined by that eclipse observation of the X-ray light curve. So now what we can do is we can apply something like this sort of what's called an ice cream model of CMEs, which is used on the sun, to sort of describe geometrically what a CME sort of vaguely looks like, and then you can use that for various other things. But so we took this sort of ice cream cone model and looked through it. We could either put it here or we could put it around here. Didn't really make much difference. And that sort of expands self-similarly, right? So that's sort of goes as 1 over t squared in terms of the column density, and we can model that and get out quantities. So we were able to derive the mass in that ice cream cone and then the likely kinetic energy by the rate at which this thing decayed, okay? And now we can put that back on our interesting diagram here. X-ray fluence along here, X-ray kinetic, CME kinetic energy along here. And here are our points with the solar relation. We've added here the Carrington event, 1859, and then the 775 AD event. But look where the Algol event is. We're like 100,000 times bigger than AD 775. We're 1 million times more energetic in X-ray flare energy than Carrington. So that sort of sets the type of scale that we're talking about here. But what does the kinetic energy look like? Well, the real error bar is rather large, but if you sort of nail it down a little bit, it comes down to look more or less along the line of extrapolation. So maybe these solar extrapolations are not too far out, but of course we have one event here with large error bars. We obviously need more of them to actually make a bit more physical sense about what may be going on. So what for the future? Well, type 2 radio bursts are probably going to be where it's at. SKA should begin to detect these. There are surveys for type 2 radio bursts ongoing right now. I think at the moment, no definitive detections, several candidates, no definitive detections. What we're doing here is developing an MHD particle sort of code that Sophia Mostu is working on. This is a beautiful image that she got in the radio. So this includes all of the, this is at 30 megahertz for a CME on the sun, includes all of the refraction effects through the solar corona. So refraction is really a significant effect when you get out down to these low radio frequencies. So hopefully this tool will enable us to interpret CMEs and actually work out what the underlying physical parameters of those CMEs are whenever we do start to look at find type 2 radio bursts. But the other one is maybe if we ever get them as the next generation X-ray missions, LINX, ARCUS, have high enough resolution spectrometers that we may be able to see that initial expansion phase through the corona as the coronal mass ejection comes through. We'll be able to see it in blue shift. The X-ray resolution is high enough. So back to those questions and some answers. So, can we extrapolate flare CME relations from the sun to active stars? Well, no, not without some modification. Suppression, that gives us a little bit of a help. But my gut feeling is we probably need to turn things over a little bit more as we go to higher and higher energy, and this is not going to be the whole thing. What fraction of L-Bol can dynamo activity extract? Well, your guess is probably as good as mine on that one. But CMEs may give us that handle, right? If most of the energy is coming out in CMEs, then that is our ceiling. That's what we need to explain. So that defines the energy. If we're looking at X-rays, then it's not enough. We don't see enough. White light, again, is a large fraction, so that certainly helps too. The last one, CMEs and active M dwarfs are close-in planets doomed. Well, let's think about it for a bit. So we got a planet around Proxima. It's sort of more than 10 times closer than we are to the sun. Proxima has stayed active for, it's still active now after 6 whatever billion years is the current age estimate. That's a long period of activity. 10 times closer goes 1 over r squared, so it's taking 100 times the CME energies that we're taking at Earth. I think the atmosphere is going to be fried. So I think CMEs and active dwarfs, because the larger ones still escape, I think close-in planetary M dwarfs have a real hard time to hold on to any volatile atmospheres. I'll stop there.
That's really exciting stuff. I have a question, but I just wanted to comment. I remember reading some time ago, and some of our planet experts may be better informed on this, that maybe it's not so bad if early during its life a planet does get fried, because later on, it starts with sterile conditions within which life can develop later on. So I've even heard this in a newspaper report on the research. Say this is great for life. So take that with 20 grains of salt. But my question has to do with the optical activity, and that is, we have tremendous optical light curves from Kepler, and now we have tests coming up. And are there distinctive enough characteristics of these CMEs that you think that, obviously through flares, as you've already described, but perhaps some additional information hidden in there at low amplitude relative to the flare, that you might actually be able to identify them with these amazing light curves at optical wavelengths?
Yeah, I think the scattered light, it's tough because you've got scattered light, right? And so there's conservation of light in a way. You don't sort of gain or lose very much. It's all optically thin. So to see any signature of CMEs in the optical, unless it's an absorption effect, which is quite difficult to do too, I think is going to be tough, really, really tough. I don't hold out too much hope from that. I did think about that. But the problem with the M dwarfs through time, right? It's because they basically lose all the volatiles. They probably, as I guess, they probably don't have any volatiles left. So there's no atmosphere left over a period of time, unless it gets replenished internally from the planet itself after a period of a few billion years,
comets
or from something else. Then maybe, right? If you can replenish the atmosphere after several billion years, when all the activity period has sort of gone down a bit, then maybe you're in for something.
Thank you.
Yeah.
Early on, you had like an equation for the mass as a function. Can you go back to that?
Yeah, sure.
So this is just linear in the X-ray luminosity.
Yeah, yeah.
All those plots you're showing seem to be way super linear.
Yeah.
So what's going on there?
Right. So there's this doesn't have there's the flare association rate, right, which folds in two. So that's another curve that is sort of factoring in there. This is sort of simplified version for illustrative purpose. But these things also give you a. This one is depending on what your limits of integration are. That sort of changes. At least the way I did it, it changes according to the X-ray luminosity of the star, right? So that sort of skews things a little bit too. So those limits of integration are not fixed for the whole plot. But the other one is the flare association rate, which goes in there at lower X-ray, lower flare energy. Something else?
So, do you have any speculation on? I mean, clearly the most active stars are active for some reason, and is it completely out of line to imagine that they're active because they have, for example, a particularly active dynamo, or that dynamo is somehow coupled more efficiently to the surface?
Yeah, it's
And
basically
generating these sorts of things. So,
Yeah.
I mean, you were saying your instinct is that this is still over-predicted at the high end, and I guess I'm just asking, what would it take for that not to be the case?
Well, the whole thing is driven by differential rotation, which is essentially proportional to rotation rate. So you got the whole thing is basically driven by rotation. So the spin down of stars over time gives you the whole thing, essentially the whole picture of why it decays and how it decays differently within star types. But if you have you're trying to generate a magnetic field with shear, essentially, at some point you reach this sort of saturation where the magnetic pressure won't allow you to do any more shearing. And that's a sort of saturation regime, which is talked about and debated a lot.
Yeah.
And the question is, at what point does that set in? And I think that's the difficult question. No one really has a good handle on how the quenching of things happen as you reach that sort of saturation point. I mean, that's one of the.
And could you imagine this being different in, for example, algal, where there's like tides driving the differential rotation as opposed to an isolated star?
That's a really good question, because you'd think that it might make a difference. If you look at binaries that are close binaries and you look at single stars rotating at the same rate, you really see no obvious difference. One example is AB Dor, single star, compare it with B471 Tor, close white dwarf, with pretty much exactly the same rotation period. They have the same X-ray luminosity. You look at their spectra and the X-rays, they look pretty much identical. So the tidal effect is probably not, it's not a first order effect. Anyway. Yeah.
Interesting.
Okay.
Well, let's thank Jeremy again. Our next speaker is Tomek Kaminsky. He did his PhD at. Let's wait a few minutes. Our next speaker is Tomek Kaminsky. He did his PhD at Nicholas Copernicus University. He's since been a postdoctoral fellow at Planck and then at ESO in Chile. And now he's an SMA fellow here at 160 Garden. We're going to hear from him today about weak mass losses in HB stars. So Tomek, thank you so much.
Thank you for inviting
There's
me.
no rush. And then immediately afterwards, we may pause for a moment, get pizza, and then come back in.
Right. So let's start easy. you know that dust is formed in many different stars on the HI diagram. Among the more massive stars, probably it's red supergiants that produce most dust, but it's also supernova explosions in which you can produce dust. And in the early universe, it's probably the supernova explosions that provided most mass of the dust. In the old universe, in a galaxy like ours, it's the low mass AGB stars that produce most of the dust. And the dust enters interstellar medium. There it's processed, and then it's used to build up a new generation of stars. So we want to understand the life cycle of dust very well. And in particular, we want to understand how it's being formed. And it's being formed in stars. AGB stars produce two types of dust, carbonaceous dust, and oxygen-rich stars produce inorganic dust, so silicates, alumina dust. And in case of carbonaceous dust, we understand more or less how it's being formed because it's essentially the same process as we have in flames here on Earth. We can study it very, very nicely, and it's just essentially production of soot. In case of oxygen-rich stars, the thermodynamics of the process is very complex, and we still don't have a good idea how it's being produced by stars very close to the photospheres. And this talk is about only one particular problem in dust formation in oxygen-rich stars. So the envelope, those plots show schematic structure of the envelope. As you go far away from the star, the temperatures drop down, the densities go down exponentially. Very close to the photosphere, you have shocks which are driven by the regular Myra-like pulsations. And those shocks actually lift up material to a point where you can form dust. Once you have dust formed, it can interact with the radiation pressure from the star and can drive wind. The terminal velocities of those winds are of about 10 kilometers per second. So molecules are formed already in the stellar photospheres in thermal equilibrium, but these are mostly diatomic molecules. More complex molecules you form in the circumstellar medium at high densities and low temperatures. And you can build up very, very complex species. Eventually, they become so large that they have properties of a solid state particle. You cannot consider it as a gas phase molecule. The fat silicate dust is formed of actually low temperatures, below 700 kelvins. And this is the silicate dust you probably associate with circumstellar envelopes. This is like forsterite and iron-type silicates. So those silicates can form efficiently in envelopes of AGB stars only if you have in the environment already small solids created which act as condensation cores. So we can condense silicates easily if you have already some solid particles created at lower temperatures, and we call those particles seeds. Those particles have to be made of abundant molecules that can withstand very high temperatures, as high as 1700 kelvins. So we still don't know what those seed particles are, and we're trying to identify what would be the best material to provide those condensation cores for silicate formation. Okay? And one way to identify those species is to make theoretical studies. As I said, the thermodynamics of the process is very complex, but nevertheless people try. And here is a result of one such study. The different colors show nucleation rates of different species of iron, silicon oxides, titanium oxides, and aluminum oxide. And the nucleation rate, so like the stickiness of the material, is shown as a function of pressure, or you can think about density and temperature. And those green rectangles show a range of parameters which we expect in this seed formation zone. Okay? So in this particular study, it was concluded that titanium oxides are very sticky in this region, so they can provide, they are good candidates to provide those seeds. Unfortunately, titanium is not very abundant species in the envelope, so you would have to condense all available titanium into solids to be able to explain all the silicates that we observe in AGB stars. Some other studies conclude that it's actually aluminum oxides that are more important, especially in those envelopes where the dust formation takes place at higher temperatures. So those theoretical studies are very difficult. There is many simplifying assumptions about the thermodynamics of the process, and they also rely on laboratory measurements which are very difficult to do, and they are then extrapolated to extreme temperatures and densities. So they are not very reliable, but definitely provide important first hints. Another way to identify those seeds would be to study the presolar grains, so grains created in AGB envelopes, which somehow survived and processed in the interstellar medium and in the presolar nebula, and ended up on the lab table where their isotopic ratios could be measured precisely. So among those presolar grains, we identified only a handful of grains that contain titanium oxides. A much larger number of grains with aluminum oxide have been identified, and indeed some of them have aluminum oxide core, which means that you have an aluminum oxide core and it has a mantle of silicates, which corresponds well to the condensation sequence I presented a moment ago. So this fits very nicely to the picture, but those studies have also lots of limitations. For instance, you can measure in the lab only the largest grains. There is a lot of grains that we are not able to measure. One other way to identify those seeds would be to try to observe them directly, for instance, by obtaining mid-infrared spectroscopy at very high angular resolutions. And such studies have been done for only a handful of stars. One such star is the GX-MON. So in this particular study, it was concluded that aluminum solids are present at radii larger than 2.5 star radii, and silicates are only seen at radii larger than 5.5. But the identification of aluminum oxide very close to the stellar photosphere is based on the fit to the 10 micrometer feature, and I guess most of you realize that you can fit to this feature different mixtures of dust, and they will fit as good as aluminum oxide. So this is not an unambiguous identification. So in my opinion, a more elegant way of identifying those seeds would be to identify the precursors, and let me explain that point in this slide. Let's assume that it's titanium oxide that produces seeds in AGB stars. Titanium is formed already in the stellar photosphere. It's being transferred to the circumstellar medium, where it can react with water and is being oxidized to titanium dioxide. The material is going away from the star, and you get more and more titanium oxide at lower temperatures thanks to this reaction. So eventually, at say 1000 kelvins and 3 stellar radii, you essentially have only titanium dioxide. Then if you go to lower temperatures, you convert this gaseous titanium oxide into solid titanium oxide, and then those particles stick together, forming dimers, trimers, and larger clusters, and of those clusters, you can form silicates. So if you want to observe now this envelope with a telescope and study only the gas phase species, you would see the precursors only. You would see TiO2 and TiO. TiO would be very close to the stellar photosphere at high temperatures, and TiO would be farther away at, say, 3 stellar radii, and it would have a temperature of about 1000 kelvins, and it would disappear in the place where you form the first solids. All right, that's the idea. The thing is that 10 years ago, we didn't have a good way to measure any of the relevant precursor species. There were no molecules observed in circumstellar envelopes that would allow such a test. Preferentially, you would like to observe those molecules at sub-millimeter wavelengths, because with ALMA, you have now the angular resolutions that would allow you to trace the abundance patterns and the depletion directly on interferometric maps. And if you look for new molecules in an oxygen-rich star, you direct your telescope to VY Canis Majoris, which is not an AGB star. It's a red supergiant that started its life as a 25 solar mass star, and now has a very high mass loss rate, 10 power minus 4. So with this mass loss rate, it accumulated this big cloud of dust and molecules. The molecules have a mass of about 1 solar mass. And if you want to look for more new molecules, this is the primary target you want to start with. This object was observed with the SMA array in a very broad frequency range, which we call a line survey at pretty decent sensitivity and angular resolution. And in this survey, we identified many molecules, but among those, the weakest features you see in the spectrum are very exotic molecules like PO, but also species that contain aluminum oxide. And this is the spectrum where, for the first time, we identified pure rotational lines of titanium dioxide and titanium oxide. And those identifications were later confirmed with the Plateau-Debye interferometer at lower frequencies. You can see the beautiful lines of TiO and many lines of TiO2. So that was a great success because it tells you that those species actually form in those stars, that you can observe them, and you can study perhaps them in AGB stars. But it happens that the data were good enough to actually try to make the first verification of this nucleation scheme in the VY kinase majoris. So, for instance, TiO emission was resolved. We could locate the emission of TiO just by studying the velocity profile of the emission. Because we observed many transitions from TiO in this line survey, we could derive the excitation temperature. It was not quite so easy for TiO, but it happens that VY kinase majoris is one of the few sources in the sky that have TiO bands in emission, which means that the TiO comes from the circumstellar envelope. And by studying the electronic optical spectra, we could derive the temperatures very well. And using VLTI, we derive the full set of parameters for both TiO and TiO2. For instance, TiO we see for up to 30 stellar radii. TiO2 is slightly more extended, and the excitation temperatures are of about 225 and 600 kelvins. So now if you want to compare it to this classical nucleation scheme, and if you assume that you have a full condensation of both titanium oxides in the envelope, you should expect that TiO and TiO2 disappear. You shouldn't see any TiO essentially at 2 stellar radii. And if you see any of those two species, they should have very high excitation temperatures, which is definitely not the case here. What we see, the set of parameters we derived agree very well with what you expect for no nucleation of titanium oxides, where you just essentially see the oxidization of TiO into TiO2 at large radii from the star. We also observed aluminum species in VY kinase majoris, which allowed the first test for aluminum condensation in the star. So again, by using rotational transitions from SMA and other 7mm facilities, combine the data with those beautiful observations of aluminum oxide in the optical spectrum. Yeah. I think I pressed it too many times. So, yeah, you can study the rotational profile of those electronic bands and get the temperature, and again we get parameters which indicate that a lot of aluminum oxide survives far away from the star, indicating that neither aluminum oxides are good candidates for SID particles in this source. So what is going on? We definitely know that there is a lot of dust produced in the star. You can see this exactly in this image because it's a scattered light image from the Hubble Space Telescope, and you can see that there is a very elaborate substructure in this nebula. It's because there are parts of the envelope that collide with each other. So there are some shocks in this environment. So we think that maybe the dust is being produced very effectively in the source, so that we don't even see those precursor species because they are so efficiently depleted right away after they appear in the envelope. But as the material is being blown by the wind away from the star, it may be destroyed by some shocks far away, and that's why we see those species going back to the gas phase. But this interpretation has definitely lots of problems as well. Today we also have ALMA observations for this guy, and we can see in detail the emission of the different relevant species for titanium oxide and for many aluminum oxides, but to interpret them is very difficult. They don't agree with any of the nucleation schemes we know, nor even the gas phase species correspond to the predictions of equilibrium chemistry in AGB stars or evolved stars. This may be related to the very large convective cells that you have on the surface of a red supergiant. So we should go for an easier source, more prototypical for AGB stars, and we decided to observe Myra, which is really the typical oxygen-rich AGB star. It's nearby. It has a typical mass loss rate of about 10⁻⁻⁷ solar masses per year. So we organized an observational campaign which included multi-epoch ALMA observations and observations at apex. We used spectra, far-infrared spectra from Herschel, and we also compiled a database of tens of spectra, optical spectra of Myra going back to 1926, which allowed us to study the variability of the different species in the star for a very long time. Just a few results. Here are maps from ALMA showing the emission of titanium oxides. TiO is fairly symmetrically distributed around the source, and it's centered on the source. From the spectra, we see that actually some part of TiO is actually infolding on the star, not only outflowing. TiO2 is much more patchy. It's not so symmetrically distributed around the star, and it's not centered on the star. But nevertheless, you can derive the beam deconvolved sizes of the emission, and you get 4 stellar radii for TiO and 5.5 for TiO2, which agrees very well with what you would expect for the star. So using the similar techniques as I showed you for VY Canis Majoris, we could characterize both oxides in the star. And here I would like to pay your attention to the abundances. For both species, we got an abundance of about 10⁻⁻⁷ with respect to hydrogen. And this is almost exactly the same order of magnitude as we expect as the elemental abundance of titanium in this envelope, which means that we used up all the titanium that is available there just to create those gas phase titanium oxides. There is nothing left for creation of solids. So the conclusion is that titanium oxides are probably irrelevant for the condensation process in Myra and probably in other evolved stars. We also observed aluminum oxide and other aluminum species, but today I would like to focus only on one map. This map was done with unprecedented resolution of 30 milliarcseconds. This was done in the first ALMA long baseline campaign. In those observations, the photosphere of the AGB star was resolved, and here it's represented by this gray ellipse. Because there is some gas of lower temperature than the photosphere between us and the star, we see absorption towards the star. And the emission that you see around the stellar disk is very patchy. This is real, and we can trace it up to about 10 stellar radii. You can also see that some of the emission is confined to this horseshoe shape or incomplete ring structure, which has a radius of about 3 stellar radii. And this is the very important region in the stellar envelope where the dust is being formed. Actually, we directly observe in different phases of the cycle hot dust being located between 2 and 3.5 Earth star. So this is exactly the region where we expect the first condensation to occur. So now when you look at the map and you make special cuts like those I'm presenting here, of course, we're showing here emission, which reflects the different excitation in the envelope and different abundances. But if we understand the excitation well in the source, you cannot have such a drop as with this black line just by pure excitation, and it must be some depletion of aluminum oxide in the envelope at about 3 stellar radii. That means that it's being consumed by some other molecules or probably even solids, and it's most tempting to think that this is that we actually witness nucleation happening in the star. Also, the amount of aluminium oxide that we see in those ALMA observations leave a lot of aluminium that can be used to create dust. If this is indeed nucleation we see here, it would indicate that any dust that is produced in the star is going to be patchy as well. And this is exactly what was observed years ago in Myra. There are clumps dust clumps in the envelope. And today we're trying to secure more contemporary observations that can be directly compared to those ALMA maps. Those are being done mostly at VLT with the gravity instrument and SPHERE. SPHERE observed already other AGB stars. For instance, here we have an image for W Hydra, which shows this clumpy structure as we would expect from those ALMA observations. So to conclude, it appears that titanium oxides are really irrelevant for the nucleation in evolved stars. Aluminium oxides seem to be more likely candidates to provide the answers we seek. Of course, there is much more to be done, and one of the things that would really push this research forward would be to characterize in the lab other gas phase species such as Al2O and so on. And this has just started in the labs, so in the SCFA labs, and the effort is led by Kelvin Lee and Kara Gottlieb. And with this, I would like to thank you for your attention.
Okay, questions for Tom? And then when we can answer.
In your ALMA image, there seemed to be an asymmetry in the distribution in that layer. What was the direction of the companion? I know the companion is far away, about 70 AU or so, but is it correlated with that or no correlation at all?
There is no correlation.
Mm-hmm.
I think I have a slide showing the location. So this thing here, this is the gray contours show the continuum of both Myra A and Myra B. So this is lower resolution than the map I showed just a moment ago. So you can see that even in this low resolution that there is some dislocation of aluminium oxide emission with respect to the continuum emission, but it doesn't have anything to do with the companion. And I bet if we make observations in a year or two, the clump would be on a completely in a random, any other random place.
I see.
And there were calculations made that showed that there should be no effect from the distant companion on this inner parts of the envelope. I mean, dynamic effect.
So you showed us first that aluminum oxides seem to not work in the left-hand majorities,
Yeah.
but then it seems to work in Myra.
Yes.
You have sort of a figure of what might be going on.
So again, we used the V-Vacancy majority just to prove the first detection. It was not the aim was not to study dust nucleation in red supergiants because they're too complicated. We don't understand where those different how those arcs are being formed. Why do you have such activity in those stars? It's probably linked to the convection on the surface of the star, but it is very poorly understood. AGB stars are much better. We have a better chance with AGB stars.
So this is a little bit out there, but we know that dust in these winds is really critical in their eventual acceleration, the dust opacity and the radiation pressure. And so if the dust formation itself is more clumpy, you might expect sort of clumpy pressure on parcels of this gas and maybe more internal structure and internal shocks in the wind. And I just wondered if you have thought about what tracers of that might be, or how we might sort of distinguish a clumpily driven wind versus a more continuous wind. And
one of these?
Honestly, I don't know how to answer this question, but I see on Astro PH that people will notice that this is quite an issue in AGB stars, and this should be taken into account when you want to explain the dust-driven winds in AGB stars. So there is this big problem in oxygen-rich stars that the absorption of photons is not enough to track those winds. That's why some people propose that it's actually scattering that is more important for those. They just not opaque enough to drive the winds. So now people understand that with those new sphere observations and other observations, it's clear that the winds are very clumpy, and this should be taken into account when trying to explain how those winds are being driven. I think people look into this, they call it porosity or
Porosity,
yeah.
okay. Interesting. Okay. Other questions for Tom?
If you don't expect any dynamical effects of the binary in Myra, you know what to ask, what about radiation effects from the fact that that source is the companion is probably UV bright?
There is no I see no indication of any impact of Myra B on the envelope of Myra A, at least the inner parts. There is, if there was like photodissociation or any other effect, we would see like a bubble, for instance, in CO. We don't see anything like that. The molecules don't seem to see the companion. And if I understand correctly, it's just sporadic activity of the Myra B that we have seen so far, right? It's not a constant UV radiation.
So you think that the horseshoe will change won't change with the orbit?
It will change randomly. I think it's more related to what is going on the surface of the star, not what is going with the companion.
Okay.
Well, let's thank both our speakers. And
Oh, sorry. Yeah.